Welcome to Empowered Learning. This is the second video in the video series on the discussion about infinite series and their uses in calculus. And so in the first video, one of the things that we went over was the basic vocabulary of what an infinite series is, and we kind of delineated what is a sequence, what is a series, what is the sum of a sequence, what is a partial sum, and how all of that relates to what infinite series actually are. We also discussed that if we wanted to find out if a series converges or not, what we would have to do is actually look at the sequence of partial sums that can be created from the original sequence, and look at that list of numbers, get it in algebraic form, and if we could find it in algebraic form, take the limit of that function in terms of n, and the limit of that existed, then we know that the corresponding infinite series would actually converge upon some number. And so that was our way of trying to figure out, well, hey, is this particular series going to add up to converge upon some number without you actually having to do it by brute force. So we also talked about geometric and harmonic series, what that looked like, and what were the conditions for where, in the case of the geometric series, it was convergent. And we also noted that the harmonic series is always divergent. And then we looked at a few examples of being able to determine whether a geometric series was convergent or divergent or not. So now we are in the part 2 video, and in the part 2 video, we need to cover some basic facts that come as a result of defining what an infinite series is and its convergence properties. And so the first basic fact that we see here is the convergence of an infinite sum. And it basically says that if we know that a particular series is convergent, then we can guarantee that the limit of the corresponding sequence as n approaches infinity goes to 0. Okay, so I'll say that again. If we know that we're looking at a particular series and that series converges upon some number, if it's known, then if we go back and look at the corresponding sequence for which the series came from, then we know that the actual limit of the algebraic form of the sequence goes to 0. Okay. Now, this is important to understand that this statement that I just said is not a biconditional statement. Okay. Meaning, and I have this note up here, that just because we say, hey, if we have a series that's convergent, then this corresponding sequence, the limit of that is going to go to 0. Okay, we can say that, but we can't say if the limit of the corresponding sequence as n approaches infinity goes to 0, then that automatically means that the corresponding series is going to be convergent. Okay, and so that's the point that I'm trying to make here in this note, because our harmonic series, which is summation of 1 over n equals 1 to infinity, this is a divergent series. Okay. But of course, if I was to take the limit as n approaches infinity of 1 over n, it would go to 0. So if I was assuming that, hey, if the sequence that makes up this harmonic series here, if the limit of that goes to 0, then the corresponding series would be convergent. That wouldn't be true, because we know that this harmonic series is actually divergent. Okay, so that's why it's important to know that we can only make this assumption, that the limit of the sequence as n approaches infinity goes to 0, if it's already known that the series that we're talking about is convergent. Okay, it doesn't work the other way around. All right, the second basic fact probably out of all three of these is, in my opinion, the most important, because it kind of gets us in the ballpark of knowing if we're looking at some infinite series that is going to be convergent or divergent. So it just kind of sets the stage to say, all right, you're going in this lane or the other lane. So here, if we take some sequence, a sub n, and let's say we do the limit of that particular sequence in its algebraic form, and that limit does not exist, meaning that it doesn't equal a real number, or if it does equal a real number but is not equal to 0, then we know that that series, corresponding series, is going to be divergent. Okay, and this is also called the nth term test for divergence. So what I've done is I've actually taken the actual way that most textbooks say it, and I've kind of broken it out here. So I'm going to say it like most textbooks will say it. So they'll say something like, unless the limit as n approaches infinity of this sequence in algebraic form goes to 0, the series here is divergent. Okay. So in essence, what this is saying here is that if we know we have a sequence that a particular series came from, and if that sequence, if we take the limit of it and it doesn't equal a real number, or it does equal a real number and is not equal to 0, or putting another way, if it equals anything other than 0, then we know that the corresponding series is going to be divergent. If the limit of the sequence goes to 0, then it is a possibility that the corresponding series may converge or it may not converge. Okay, so that is what basic fact 2 is trying to communicate to us. And I'll say it again. So for basic fact 2, if we know that the limit of if the limit of the corresponding sequence as n approaches infinity is equal to 0, then there is a chance that the corresponding series may or may not converge. If it's anything other than that, then we know that it's definitely going to diverge. Okay, and so that's what they mean by unless the limit of the sequence as n approaches infinity equals 0, then the series is divergent. And when we unpack, well, unless this part, that means that either your limit is not equal to a real number or it is equal to a real number that is not 0. Okay, and so that is what that basic fact is talking about. All right, so basic fact number 3. This one I call the common sense basic fact because it just basically outlines the linearity properties. So here, if we had two series and we know that both of these series are convergent, then the following series should also be convergent. So if we're doing a non-zero constant multiple of the sequence that we originally started off with, and we wanted to make a series out of that, then of course this will automatically be convergent, because again, all we can do is we can just factor out that C, and we would have this result here. And of course, if this converges upon some number, that number times C is also going to be another number. Okay. Now, of course, if these two series converge, then the sum of the two sequences, if we formed a new sequence out of that, that would converge. And if we formed a sequence out of the difference of both of those sequences, and we made a series out of that, that would converge. Okay. Now, basic fact number 3b says here that it's, of course, completes the linearity property parts of this. So, like I was trying to say here, we know that we could take this and rewrite it this way. And we could take the sum of difference and also rewrite it this way. So what part A basically says is that if I wanted to form a series from this sequence, or from that sequence, knowing that I have two series that are already convergent where their corresponding sequences are composed of the A sub n and the B sub n, then that means that I automatically know that this particular series, that particular series, and that particular series is also going to be convergent. The part B portion here just tells me how I can actually rewrite this particular series and how I can rewrite this series. And of course, if this is already convergent, then of course you're just saying, hey, this goes towards some number times C. And of course here, if both of these series are convergent, then of course it's going to follow suit that if I add the result of two convergent series or subtract one convergent series from another, that's also going to converge upon some number. Okay. All right. So now we're going to do some examples using what we know about our geometric series and harmonic series along with these basic facts. Okay. So for our first example here, we want to look at this particular series to see whether it converges or not. Well, we know from our basic facts above, we could rewrite this 1 divided by 2n as just 1/2 times 1 over n. Of course, this could be looked at as the C. This could be looked at as the A sub n. So now this would be C times summation of A sub n. And of course, here we know that the summation of 1 over n, or the series, that's composed of 1 over n from n equals 1 to infinity. That's the harmonic series, and by definition, we know it's divergent. So that means that this corresponding series will be divergent as well. Okay. All right, so example B. So example B, notice that we have the sum of two sequences here. So we can think of this like an A sub n, think of this as a B sub n. So notice here that for this A sub n, that we could actually work with this on its own to look something like a geometric series. However, this B sub n, the 1 divided by n times n plus 1, we see that it has the properties of a harmonic series, but it's not exactly a harmonic series. So that's the iffy part in this particular example here. So what we need to do is use our basic facts to say that, hey, if we have the sum of two sequences and we want to make a series out of that, what we need to do is figure out, is this separate series going to converge? And is this separate series going to converge? Of course, if both of them converge, then we know that that the new series that we're trying to look at, this infinite series, will also converge. Now, if we analyze the first term, or the first sum that we want to look at, we see here that this 1 divided by e raised to the n, we could rewrite as 1 divided by e raised to the 1 times e raised to the n minus 1. So I'm just basically splitting out the fact here that we could rewrite n that way. Okay. And so by doing that, this allows me, using my exponential rules, to have just 1 over e here, and then times 1 over e raised to the n minus 1. And of course, 1 raised to the anything other than infinity is just 1. So we could also assume this. And thus, using our exponential rules, we can have 1 divided by e raised to the n minus 1. And so because of that, we know that this particular series can be written in this form of a raised to the a times r raised to the n minus 1. And of course, that's in geometric series form. And 1 over e is going to be a number strictly in between 0 and 1, because, again, e is approximately 2.71, and 1 divided by 2.71 is surely in between negative 1 and 1. So because of that, we know that this first term here is going to be a geometric series, and we know that it's going to be convergent. Okay, so we know that. We also know that the sum of that particular series, or the number is going to converge to, is just going to be 1 over e minus 1, because of course if we use this a divided by 1 minus r, where a is 1 over e, and so is r, then of course we can just multiply numerator and denominator here by e, and we will get this 1 over e minus 1. So we know that this first term is good. So the second term is the one that we're a little bit worried about. So we need to do some work on that. So since we see that this corresponding sequence here is not exactly the harmonic series, we need to break it out by using partial fractions here. And part of the reason for that is we know here, if we do partial fractions, we know that if we look at this as another a sub n and b sub n, this could be looked at as a harmonic series depending upon what a is. Okay, so I do all the tricks and stuff for getting what a and b are going to be real easy. And of course we have this here. If we do the same thing for b, we end up getting negative 1. And so now we know that this could be expressed this way. Okay. Now, one thing I will say here is that once we're at this point, some of you may be tempted to say, oh, look, we know that a is a positive 1, so that's going to be a 1 over n there. And because of that, what we can do is we can split this up now and say, all right, well, we have this particular series here, and then this would be a minus. We have this series here, and because this one is the harmonic series and it diverges, then that means everything else is going to diverge too. Okay. Now, the issue with thinking that is that we're kind of misinterpreting what our basic facts say. Okay, and I'm going to go back to them to kind of make my point here. So if we look back here at basic fact number 3, and 3a in particular, notice that the first thing it says here is that if we know that both of those separate series are convergent series, then we can say the following 3 things. Okay, meaning that these particular series will also be convergent. The fact that what we're actually dealing with is a situation where one of the corresponding series would actually be divergent, that automatically rules out us being able to use basic fact number 3. We can't use it because what we're actually considering is a series that looks like this and a series that looks like this. Okay. And of course, we know this one's divergent, but we don't know if this one's divergent or not. Okay. But here, to be able to even use this, we have to know that both of the series that we're talking about is convergent. And again, since we don't know that, we can't use that basic fact. So we're kind of trapped at this point in using this particular basic fact. So we're going to have to do the best that we can with the other 2 basic facts. So we're going to have to do our best with basic fact number 1 and basic fact number 2 and some of the other things that we talked about earlier. Okay, so we're in a situation here where we could express our sequence here in another way as the difference in between 1 over n and 1 over n plus 1. And again, this is not going to fit geometric series, so can't use that. Because of the fact that we have an extra term here, we can't just assume that it's all the harmonic series. So that's not going to work. And so what we actually have to do now is investigate what this particular sequence is going to act like. Okay. And so if we look at this, again, you see here that I'm stating that this particular series that we're referring to is not geometric and is not harmonic. Okay. It's neither one of those series. So for us to test the convergence of this particular series here, we're going to have to find an expression for the nth term of the sequence of partial sums. Okay. Now, what does that mean? It takes us back to what we talked about earlier. If I want to know if a corresponding series is convergent or not, what I could do is take the limit of the sequence of partial sums for that particular series. And if the sequence of partial sums, if the limit of that is going to exist, then that means that this corresponding series here will actually converge. Now, what this ends up being whenever we have to do this whole thing of investigating what the sequence of partial sums would be to get some algebraic form of it, this particular case is called a telescoping series, because we have to list out terms and kind of telescope in to see, well, for the nth term, what is this going to look like? And so if we look here, if I was to let n equal 1, I would have what's in this first parenthesis here. So I would just have 1 here, 1 there. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. Okay. If I did it again with n equals 2, then of course this is 2, this is 2. So I have 2 here, 3 there. Okay. And of course you can kind of see the pattern as we move forward here. If we keep on going, when we get to the nth term, so when n is equal to n, then it's just going to look like this. And if we go and look back at everything, we have a minus 1/2 and a positive 1/2 that cancel. We have a minus 1/3 and a positive 1/3 that cancels. Okay, so you can kind of see as we list out these terms, this 1 is not going anywhere, but everything else is. So we go ahead and list out the nth term. What we end up knowing at the end of the day is that every term is going to cancel except for this last one here. Okay. So if you list it out on your own, you'll actually see that. So if we wanted to go for the nth term, we just know that it's going to be 1 minus 1 divided by n plus 1. And so this would be our nth term of our sequence of partial sums. Okay. And so now if we take the limit of this sequence of partial sums, we see that it actually ends up equaling a real number. And thus, since the limit of the sequence of partial sums exists, that means that the corresponding series that sequence of partial sums was made from is going to be convergent. Okay. And so we see from here that if we keep on doing this, that this converges, and the value that's going to converge to is whatever this limit is, which is 1. So therefore we have 2 convergent series. And of course we proved it differently. So we saw, hey, we could take this and rewrite it this way. And this was the geometric series. This one was a telescoping series, but both of them ended up being convergent. And of course, they converged their respective numbers. And I just did some fancy footwork here to make this just be all under one quotient. So the actual sum of that particular series would just be e divided by e minus 1. All right, let's move forward here. All right, so again, before we move to the next example, please note here that this series that we looked at is an example of what we call a telescoping series. And we're going to see that again. So for this next example here, we want to do the same thing. We want to see whether this particular series converges or not, okay? Whether it converges or diverges. So the first thing that we need to realize here is we can simply look at a series and start off by using the nth term for divergence theorem. So the nth term test or theorem for divergence here is actually basic fact number 2. And if you remember here, the compressed way, or I would say the short way of saying it, is that if we were to take the limit of the underlying sequence that the series is made from, and if this particular limit did not equal 0, then we know that the corresponding series will be divergent automatically. Okay, so that's kind of like our way out. Hey, whatever the sequence that the series was made from, just take the limit of that. If the limit is equal to 0, then it may have a chance of converging or diverging, and we have to find some other way to show that. If it equals anything else other than 0, we know automatically diverge. Done, finished, see you later. Okay, and so that's what we're going to do in this next example. All right, so main thing here is that we need to note, or we should say let, probably. That's probably a better way to say that. So we're going to let a sub n equal e raised to the n over n squared. So then we'll just take the limit as it approaches infinity of e raised to the n over n squared. And again, what we are looking for is if this limit of the sequence that this series is made from, if it is equal to anything other than 0, we automatically know that the series is divergent. Okay? Automatically know. So here, if we put on our pre-calculus hats here, notice that the function e raised to the n, even though it's a sequence, it is going to grow faster than the function n squared. Okay, just by sheer that exponential functions always grow faster than power functions. So we know that this particular limit here should end up equaling infinity, but just in case you're not convinced of that, I will go ahead and use L'Hopital's rule to show you that. So of course, if I plugged in infinity here for n and n in the numerator and denominator, I would get an infinity over infinity case, which lets me know I can use L'Hopital's rule. And L'Hopital's rule basically says I need to take the derivative of the numerator and denominator separately. So if I do that, I see here that, again, I plug in infinity, I'm going to get infinity over infinity again. So what that means is I am going to have to use L'Hopital's rule one more time. So I take the derivative of the numerator, which of course is just going to be itself. Take the derivative of the denominator, ends up being 2. And now when I plug in infinity, I have e to the infinity over 2, which is just infinity over 2, which just goes to infinity. Okay. And so because of this, because my limit did not equal 0, okay, I know that this particular series here is going to diverge. So e raised to the n over n squared diverges. So we already know that. Now, of course, if we just looked at this and we just said, hey, the higher values of n I plug in, note that the numerator is going to grow much faster, or the numbers are going to be much higher than the ones in the denominator. So that's a very simple way of being able to show that, hey, this particular series is not going to converge. Okay. All right, so let's look at this next example here. And so for this one, notice that we can rewrite this particular series this way. We factor the denominator here. So n minus 1 times n plus 1. And so with that, of course, we have basically the product of two functions. And that's not going to help us out any. So this is one of these cases where it's probably advantageous for us to go ahead and do partial fraction expansion. Okay. So we're going to see what 2 divided by the product of n minus 1 and n plus 1 would be as two sums. Okay. So here we know that A is just going to be 2 divided by n minus 1 times n plus 1. And since A is over the n minus 1, we know that we have to multiply by n minus 1 and then evaluate that result by n equals 1, because 1 is the thing that makes the number that makes n minus 1 go to 0. So we have that. Get rid of this. It's essentially just 2 raised to the n plus 1 evaluated at 1. So that just ends up being 1. So we do the same thing for B. And then this time, because the B is over the n plus 1, this will be n plus 1. But now we have n is equal to minus 1 there. Of course, this will reduce to 1. And we just have 2 divided by n minus 1, where n is equal to negative 1. And this ends up being a negative 1 there. So, therefore, we know that our series that we're dealing with now can be rewritten as 1 over n minus 1 minus 1 over n plus 1. Okay. And of course, both terms that we have or in our series, so in other words, the 1 over n minus 1 and the 1 over n plus 1, both of these are technically not harmonic series. So because of that, I am going to have to list out some terms to see what my nth term of the sequence of partial sums would be. Okay. So here, if I was to let n equal 2, because that's where this one starts at, this would be 1 divided by 2 minus 1 minus 2 plus 1. Okay. And then we would do it again, let n equals 3. And then we'll do it again, let n equals 4. And then we can keep on going. And then, of course, if I did, let's say if I was going to do it to the nth time, a time before that would be n minus 1. So let's say this is going to be n minus 1 minus 1 minus n minus 1 plus 1 And then, of course, the very last one here, and I'm just going to write it right here, it's just going to be plus, and I'll have 1 over n minus 1 minus 1 over n plus 1. Okay. All right, and I think I have a slight mistake here. I think that should be minus. Yeah. Okay. All right, so now that we have that, now we can actually start listing what's going on here. So we could say this is just, this first term is 1 minus 1/3 plus, we'll have 1/2 minus 1/4 plus 1/3 minus 1/5 plus. And so now you can sort of see the pattern here. So if you think of this as 1 over 1, then of course the difference in between each of these is 2, denominators is 2. And of course for each term, notice, and I'll circle this to kind of make my point, this denominator starts with 1, that one starts with 2, that one starts with 3. So we can kind of recreate this pattern here to see what's going on. So this would be 1/4, and this should be minus 1/6. And next this would be 1/5 minus 1/7. And then this would, so at this point I think we have enough to kind of see what's going on there. So let's erase this, and then we could of course do this whole deal, and this will be 1 minus n minus 2 minus 1 over n, and then this is plus 1 over n minus 1 minus 1 over n plus 1. Okay, and so again, our goal here is to kind of get a pattern here, see what's going on, and then express what we're looking at here as a sequence of partial sums, all that in terms of n. So if I come here, notice that this negative 1/3 and this positive 1/3, all of that is going to cancel to 0. Okay. And so notice, I'll go ahead and write this too, that this happens, remember this is n equals 1, this is n equals 2, this is n equals 3. Okay, so at the n equals 3 point, we have something canceling. So if we keep on going here, we'll see that this minus 1/4 and this positive 1/4 will end up canceling as well. And that happens when we have n is equal to 4. And if we keep on going some more, we see that here we have this 1/5 here, and this 1/5 here cancel. And that happens when n is equal to 5. All right, so at this point, we have enough to be able to see the pattern, but we need to be able to extract it out properly. So what I'm going to do to make this a little bit easier for us to see is I'm actually going to erase this part, because this may be a little misleading here. And what we'll do is we'll just let this be assumed to continue on. So we're just going to do the 3 dots here, and we're going to look at what we currently have. Okay, and I'm going to look at this in terms of n being 5. So if I look at it this way, then notice that what I have not canceled out, I haven't canceled out the 1 that's right here, having canceled out the 1/2. And of course, I have these two terms here. Now, if I write this out for what the nth term of the sequence would look like at any given value of n here, and that's why I was going to do a plus. I'm going to write this right here. I know that for, well, let me not write it like that. So we'll just make an assumption here. So here we know that the nth sum of partial sums of this particular sequence here that we're writing, we know that we're going to keep the 1 that's here. We know we're going to keep the 1/2 that's here. And for these two, remember that n is 5. Okay? So according to n being 5, 6 is 1 more than 5. So if I wanted to rewrite this could be 5 plus 1. And then I could do minus. And of course, 7 is 2 more than 5. Okay? And so finally, if I was to say, all right, if n is 5, I replace my 5s with n, then what I'm going to have in the denominator here is going to be n plus 1, and I'm going to have n plus 2. And so this is what my nth partial sum of this particular sequence would look like. Okay. Now, of course, I could simplify this and make this 1 plus 1/2, 3 over 2, and then just minus 1 over n plus 1 times 1 over n plus 2. And so our goal here is that we would now want to figure out, well, what is going to be the limit of this sequence of partial sums. Okay, so from here, the goal is to figure out what is that. And if that limit exists, then I know that the corresponding sequence that I was referring to, I'll know that that particular sequence will converge. Okay. So again, because I have an expression for the sequence of partial sums that comes from this n minus 1 minus n plus 1 sequence, because I have that, if the limit of this expression here, if it actually exists, meaning that it equals a real number, then I know that this particular sequence that I've been considering from the beginning, I know that that particular sequence will converge. Okay. And so what it will converge to is whatever this particular limit will end up being. All right, so now here comes the easy part. All we need to do is evaluate the limit of our sequence of partial sums. So therefore, we have limit as n approaches infinity, 3 over 2 minus 1 over n plus 1 minus 1 over n plus 2. Of course, here, this one's real easy. We can just plug in infinity wherever we see n. Of course, we know that both of these in terms of limits is going to go to 0. And thus, the limit does equal to a real number, so therefore exists. Therefore, this sequence and we had 1 over n minus 1 times 1 over n plus 1, which is the same as saying let's go ahead and write this here, and equals 2 to infinity of 2 over n squared minus 1. So I believe that's what we originally had to begin with. Yep. Will converge. And we're just going to say it converges to 3/2 because that's what the limit of the sequence of partial sums actually ends up converging to. And so that is another example of a telescoping series and how we use it to be able to figure out if a particular series will converge upon some number or not. Okay, so in our next example here, what we want to do is, again, determine whether this particular series that we're looking at is going to be convergent or divergent. Just kind of looking at its form here, we see some fraction raised to the power of n. So that looks something like a geometric series, but it's not quite in the form that we're used to seeing it in. So we want to try to match it up as exact as we can, because if it is end up being a geometric series, then we want to know what the a is and what the r is to be able to find out what its sum that it converges to. So we know that regular geometric series normally looks something like this. So we have summation from n equals 1 to infinity of a times r raised to the n minus 1. Okay? So we need to be able to figure out what is our a and what is our r in this case. So here, notice that we have n equals 0 here. And of course, if we plug that in here, that will give us 1 as a result. Okay. So we know that that very first term we want to be a 1. So we're just going to say summation here, and we're going to say 1. Okay. Because that's what a is actually the first term. So with that being said now, we want this to be n equals 1, okay, because we need that. And of course, what that means for me here is that I need to rewrite this as 3 divided by square root of 11. And instead of this being n, this is just going to be n minus 1. Okay. And the reason for that is that if I plug in a 1 here, so I'll do a different color here just to kind of make my point. If I plug in 1 right here, then of course this 3 divided by square root of 11 raised to the 0 is just going to be 1. And 1 times 1 will give me 1, which is exactly what I would get the very first time I plug in 0 into here. Okay. Now, of course, if I plugged in 1 into here, meaning going to the second term, if I plugged in a 1 right here, then this would just be 3 divided by square root of 11. And the equivalent of that being here, plugging in a 1 here, would be like plugging in a 2 here. Of course, I would have 1 times 3 divided by square root of 11 raised to the 2 minus 1, which is just 3 divided by square root of 11 raised to the 1, which is just 3 divided by square root of 11. So I have the form that I'm looking for there. Okay. So because of that, we now know that this is going to fit this form. A times r raised to the n minus 1, or of course where a is 1, and my value of r is going to be 3 divided by square root of 11. Okay, and square root of 11 is a little bit more than square root of 9, which is 3. So we know that square root of 11 is higher than 3. So that means 3 divided by a number that is higher than 3 is going to be a number that's in between -1 and 1. So here we know that this particular number here is in between -1 and 1. So this means that we have a geoseries that converges. Okay. And because of that, we know that this particular series, and I'm going to write it in this form, this particular series will converge to A divided by 1 minus R, and A of course is 1, and R is going to be 3 divided by square root of 11. So here, use a different color there. We can multiply both the numerator and denominator by square root of 11, just to make this look a little bit nicer. And this will be square root of 11 over square root of 11 minus 3. And so this will end up being that sum. You could write it like this. If you are the type that you don't like having irrational numbers in the denominator, of course you could go ahead and rationalize the denominator if you like. And I'll go ahead and do that just for those of you that are kind of on a purist side there, that need to see that to make you feel happy on the inside. I'll go ahead and do it. So here, so you have to multiply by square root of 11 plus 3. Of course, denominator here will just end up being square root of 11 squared minus 3 squared. And up top, we'll just multiply square root of 11 times both terms here, which would be 11 plus 3 times square root of 11. And we'll have 11 plus 3 times square root of 11. And this will just be 11 minus 9. And final answer there would be 11 plus 3 times square root of 11, all that over 2. And so that is what this particular series, the number that it would converge to if we kept on adding up all the numbers that is in this corresponding sequence here. Okay, so for our last example in this particular video here, we are going to look at this particular series and see whether it is convergent or divergent. And so just looking at this, the fact that we have sine in here, we know sine kind of oscillates back and forth. So this particular sequence that's making up this series will kind of have, you know, this shape to it here. So we just kind of just using our context clues there, we would say, hey, this thing may end up being divergent. But again, we want to actually show that instead of just guessing it. So to do that, we notice that because we have sine of, you know, some expression in here, we're not going to be able to characterize this as a geometric series. Of course, it's not going to be harmonic either. Okay, so it's, I don't know why my pen's hanging up like that. But yeah, it's not going to be harmonic either. It did the same exact thing. So let's try that one more time. Okay, there we go. All right, it's not harmonic. Because we don't have multiple terms here, it's not going to be anything that is telescoping either. So we're kind of on out there in limbo. Okay. Now, whenever we have a situation like this, we have two options. One is we can just list out a bunch of terms here to kind of see how it acts, kind of like how we would for the telescoping series, and hope that we get something. Or we could fast track to our nth term test for divergence. Okay. And so if you remember, the nth term test or theorem for divergence basically says that unless the limit of the sequence in which our series is formed from goes to 0, we automatically know that that particular series is going to diverge. Okay. So here, what we need to do is we need to evaluate the limit as n approaches infinity of our actual sequence here. Okay. Now, to do that, notice that this sequence is actually a composite sequence. So it's a sequence of a sequence. And going back to Cal A, we know that sine is defined, or sine is defined for all real numbers. And of course, because of that, and we're taking the limit of basically a composition function, our limit laws allow us to be able to take the limit of sine of the inside function to figure out what the limit of this composition function will be. Okay. So we cover here, and now we're faced with actually evaluating this limit. Okay. So now coming from here, of course, we have understood pi over 2. That is going to be a factor that we can factor outside that limit operator there. So we'll have sine, and this is pi over 2. And this will be limit n approaches infinity of, and now we just have 14n plus 1. Of course, here, if we plug in infinity for n there, what we're going to see is that we essentially have 14 times infinity plus 1, which this is just another way of saying infinity. And of course, infinity times pi over 2 is just itself going to be infinity. And sine of infinity is going to be does not exist. And again, the reason for that is, of course, sine is a function that is going like this, and in terms of sequence, it's just going back and forth. So it's not going to ever behave like it's going to one thing. So because of that, we say that it does not exist. And since here our limit did not equal 0, we know by basic fact 2, that our series is going to diverge. And I'll just say here our series diverges. All right, so this concludes the examples for this part 2 video on talking about infinite series and how we use it in calculus. So the part 3 video that I'm going to do for you is going to go over more examples, but we're going to see how we would actually take those examples of taking rational numbers in their repeating decimal form, and we're going to write them as a fraction. So we're going to do that, and of course we'll close out with some more examples of trying to figure out whether a particular series converges or diverges. So I'll see you in the part 3 video.